I'm sure most of you are very tired of hearing me introduce myself over the past 2 weeks, but I'm going to do it again. My name is Aidan Keaveney. I graduated from here about 4 weeks ago, and now I work here. So this project was conducted in the same program that you guys are in, the SCRIPT program here at UNC-Chapel Hill, and I continued this into the school year through the mentorship program. I worked with the Experimental Nuclear and Astroparticle Physics group at UNC-Chapel Hill. Principal investigator, which is Dr. John Wilkerson. And to start, I want to start with the most important photograph that humanity has ever taken, in my opinion. This is called the Hubble Ultra Deep Field. So what astronomers did was they pointed the most powerful telescope that humans have ever created, the Hubble Space Telescope. And they pointed at the darkest part of the night sky. A size of the night sky that's about the size of a grain of sand held up at arm's length, the darkest part of the night sky. And they took a 14-day long exposure, and this is the picture that they got. This is the darkest part of the night sky. Like, what does the brightest part of the night sky look like, right? So this is just sort of indicative of just how much that there is, how much exists, and how much that we don't understand. And in my opinion, the quest of sort of physics and science and humanity is to understand all of this, to understand that which we don't know, to sort of investigate those most fundamental questions about the universe. And the groups that are working hardest to answer those most fundamental questions are called rare event searches. Rare events are exceptionally infrequent and generally only theorized processes that, if found, could provide answers to those most fundamental questions about the universe. So, if we're a good example that a lot of you I'm sure have heard of is dark matter. If we were to understand what dark matter is and how it works, we would understand sort of the structure of the universe and why galaxies move the way they do. That's one of the big questions in astrophysics right now. Another one that I'm sure less of you have heard of is neutrinos double beta decay. And it's not particularly important what it is for this presentation, but what it means is that if it were found, it could provide an answer to why we live in a universe dominated by matter rather than antimatter. Because it's simulated that at the beginning of the universe, there is an equal amount of matter and antimatter. But when matter and antimatter collide, they annihilate one another. So why hasn't the universe just annihilated itself? So neutrinos double beta decay could have produced an asymmetry between matter and antimatter. So that could sort of be why the universe, exists, why it has evolved the way it has. And one thing that's really important to rare event searches is the reduction of environmental or background radiation. So background radiation is any event or signal that a detector detects, or as we say in physics, a detector sees, that isn't the signal that it's looking for. So in a rare event search, like if we're looking for dark matter, any signal that the detector sees that isn't dark matter is background radiation. Or in a neutrinos double beta decay search, any signal that isn't neutrinos double beta decay is background. We want to get rid of as much background radiation as possible, because if we're looking for a rare event, which is an exceptionally infrequent and small and precise energy signal that's really hard to find, if we're looking for that and there are so many other energy signals everywhere, we won't be able to point to a particular energy signal and say, that's a rare event. And I know it's a rare event because it can't be anything else. But if you reduce background radiation enough, especially in the area where we expect the rare event to occur, the energy region for that event to occur, we could potentially point to an energy signal and say, that's the rare event. And I know it is because there's nothing else that it could possibly be. So that's why we want to reduce background radiation in rare event searches as much as possible. And one particular aspect of reducing background radiation is building your experiment out of radio-pure materials, or not radioactive materials. So a good example, or a good analogy for this, is if you're trying to hear a pin drop at a Kiss concert, you wouldn't build a soundproof room out of speakers playing Kiss music, right? If you're designing a rare event search that's designed to reduce background radiation, you wouldn't build your experiment out of radioactive materials, because then it'll be contributing to its own background radiation. And the materials that we want to build out of are not just radio pure, they're extremely radio pure. So just some common materials in this table. As many of you know, bananas are radioactive. They decay at 15 becquerels, or decays per second. the human body at 300 becquerels, and standard building material, 5,000 becquerels, and standard building materials at 300. But electroformed copper, which is a common rare event search material, is on the order of 1 microbecquerel. So it's really, really clean or radio pure. So when you're designing a rare event search or the apparatus to build your experiments out of, you want to make sure that the materials that you're going to build it out of are radio pure enough so that they won't sort of destroy your background goal or sensitivity to a potential rare event. And a system to test the radioactivity of materials, it's called a radioassay system. So a radioassay system will measure, and it will measure the radioactivity of any samples that you put inside of it. And we want to know the radioactivity of materials before we put them inside a rare event search, so that it's not, more radioactive than we expect. So before I go any further, I just want to be clear, this is not a rare event search. I get that a lot. It's like, so what, are you looking for dark matter in this? No. This is just a tool for rare event searches to use to prepare for their experiments. So that's what the rest of this presentation is going to be about, is this radioassay system. But a lot of the principles that I've talked about already still sort of apply to the radioassay system. Because if you're trying to quantify the radioactivity of a material, when you put a material inside a radioassay system, you want to be able to take an energy spectrum and then point to a signal and say, I know that signal is coming from the sample because it couldn't be coming from anything else. There's no background getting in the way. So you need to reduce as much radiation as possible. Specifically at these elevations, by these elevations I mean the basement of the physics building at UNC. There are 3 forms of radiation we want to mitigate. Gamma rays, which are high energy photons or light. Neutrons, which are commonly found in the nuclei of atoms but can just sort of be flying around. And muons, which are electrons with slightly more mass. And each of these forms of radiation is blocked by a particular material. So for example, gamma rays are stopped by lead. Neutrons can be scattered or absorbed by borated polyethylene, which is just plastic with boron inside of it. Muons can't be blocked because they're too sort of attenuating. They go through stuff too much. But they can be identified or detected by plastic scintillator panels. And then we use electroformed copper as a support material because, like I said a couple of slides ago, electroformed copper is extraordinarily radiopure, on the order of 1 microbecquerel. But these materials must also work together, because when, for example, polyethylene absorbs a neutron, it can emit a gamma ray. But when muons pass through lead, it can knock out the neutron. So polyethylene and lead sort of have to go, they have to alternate with one another to block as much radiation as possible. And then another way that these layers work together, which I'll talk more on this slide, is a 2-layer muon veto. So in a standard radioassay system that's far deeper underground than the one that we're building, there will be way fewer muons. So we wouldn't need as much plastic scintillator. But we need 2 layers here to make sure that we detect all of the muons that are going to be passing through it, because as you increase altitude, you would increase the flux of muons, or the amount of muons that are in your system. So you have 2 layers of these, and there are a couple of benefits we get out of this. We can identify muons with more precision, both with respect to time and quantity, because we'll know their speed because we have 2 different points of reference. And any muons that pass through one layer but not the other, we'll still be able to detect. And we can rule out gamma rays that accidentally excite the plastic scintillator panels. So we accidentally detect gamma rays, we can rule those out as potential muon events. So this is the system itself. This is a cross-sectional image of it. The green thing is in the center is the detector, which I'll talk more about a little bit later on. But of course, the muon veto is in blue. That's of course blocking the muons. Lead is in gray, and that's stopping gamma rays. There's 4 inches of that. There is, 6 inches of that. There's 8 inches of borated polyethylene for neutron blocking. And copper is in the orange, and that sort of varies because it depends on where you need the most support, particularly around plastic scintillator panels because those break easily. It's about a 5-foot cube, which looking at this, you kind of wouldn't expect. It's not actually that big. And that was sort of a problem for me as I was designing. I was like, I'm thinking this is way bigger than it actually is. But it doesn't need to be that big. And it's about 17,350 kilograms. which, if you're curious, is about 8,000 pounds. It's the lead. Yeah. So I have 3 more things that I need to talk about. First, how are we going to get samples inside this thing? It's 8,000 pounds. How do you move all of it to put a sample inside? So this is sort of a very low-quality GIF or GIF of how we get samples inside. The thing that's moving the most, that's coming off of that block right now, that's the sample chamber. We put a sample inside of there, and then we slide it onto that middle part, which is called the removable shield block. That's raised and lowered by a winch that would normally be used for lifting cars, actually. And then we slide that plastic simulator back over it, put it back down, and we run all of it. And then when we're done, we move the simulator again, pull out the removable shield block, pull out the sample chamber, pull out the sample, and then you're good to go. Now there's 2 more things to talk about, and I know a lot of this is sort of dense. This is a little bit more dense, but I promise we'll get through it. The first part is the detector. So I want to thank Jesse for talking about electric fields a little bit, because that comes into play here. When radiation passes through germanium, it knocks electrons out of its lattice structure. And if you apply a voltage difference across that detector, the electrons will move accordingly. And once the electrons reach what's called the readout contact, we can measure the magnitude of the electric charge that moved, and we can measure when that electric charge moved. So that gets at both how much radiation passed through the detector and when it passed through the detector. And those 2 points of measurement are both really, really important for understanding the radioactivity of the material. So, and the last part of this is the liquid nitrogen dewar, which is the big blue thing. I'm sure many of you have been wondering what that is. So there's liquid nitrogen inside of it, and it flows liquid nitrogen through the copper crossarm into the detector. And the reason we do that is germanium is a semiconductor, which means that there's already electrons free-flowing outside of its lattice structure. So if you were to apply a voltage difference across it, the electrons would already move and would induce a signal that isn't indicative of any radiation whatsoever. So if you cool it to the temperature of liquid nitrogen, which is 77 Kelvin, or very cold, those electrons won't move. So you won't get any signals that aren't from radiation. So that's how the detector works. And that liquid nitrogen provides one more service, which is once it's done flowing through the detector, we let it boil, which isn't hard. And that nitrogen gas pressurizes the chamber inside the radioassay system, which keeps out all other gases. Anything else that might set up the detector, particularly radon gas, which is very common inside basements. And like I said earlier, this is going to be inside the basement of the physics building at UNC. So there's a lot of radon gas in there because it's really old. So yeah, so we take an energy spectrum, we subtract any background that we know is there from doing a background round earlier, and that's how we quantify a sample's radioactivity. So I know that was pretty dense, but we're through it. So there are a few things that we're still working on. One is determining how many muons there are at Phillips Hall at UNC. That's what that first bullet point is. We're also simulating the system. Actually, an undergraduate student is doing that at UNC right now. Is doing that in JONC4 computer simulations. That'll help us understand how good the system is. Our goal and our expected sensitivity is a very abstract number, 100 microbecquerels per kilogram, which it isn't really important what that number is, but it is important to understand that that is comparable to systems far deeper underground with far bigger radiation shields. So this is a very efficient system, even though it's very small. And then we need to actually get materials and start building it. So why now? Why is any of this important? So the reason this is important is that coming into the field of rare event searches, specifically the neutrinos double beta decay field in the next few years, is the Large Enriched Germanium Experiment for Neutrinoless Double Beta Decay, or LEGEND. And it is going to be the closest experiment to finding neutrinoless double beta decay, or it might actually find neutrinoless double beta decay ever in the field of rare event searches. This is the closest that we've ever gotten. And it has the lowest background goals, it has the highest sensitivity goals. So it's going to be really, really important. So before it gets started, it needs a radioassay system on hand to quantify the radioactivity of potential materials to build the experiment out of, because these need to be the cleanest materials that we've ever found. And the primary collaborator on Legend is the Experimental Nuclear and Astroparticle Physics Group at UNC, which is the lab I did this research for. So that's why all of this is important. So I'd like to thank Carolina Livery Delivery Service for taking me to UNC all the time, the Borough's Welcome Fund for funding the mentorship program, Dr. Abineri, Mr. Warren, and Dr. Shoemaker for all their support, the members of the ENAP, especially Dr. Wilkerson, and the world's greatest grad students, Chris and Anna, and Matthew Bush, who's a staff engineer at Duke, and the NCSSM Foundation and NCSSM.